A fault the length of California has been completely frozen for over 300 years. Every year it stays locked. Pressure builds. Every year it does not break. The next event gets worse. Scientists just recorded fresh earthquakes along its edge, tremors deep underground, slow shifts nobody can feel, and 2 recent quakes that lined up in a way that made researchers stop and stare. We are going to cover the hidden mechanics of this fault, the night in 1700 that dropped the coastline into the sea, the bowl of jello effect threatening Seattle and Portland, and the one question science still cannot answer. If you enjoy this, subscribe. We are just getting started. Brace yourselves. We begin. A 400-mile crack runs along the floor of the Pacific Ocean, and most people living above it have no idea it exists. It stretches from Vancouver Island in Canada all the way down to Northern California. Below the water, below the seafloor, 2 massive slabs of the Earth's crust are pressed against each other. One is trying to slide under the other. And for over 300 years, neither one has moved. That stillness is the problem. When tectonic plates grind against each other slowly, they release stress in small, regular earthquakes. You feel a tremor, the ground settles, and the pressure drops. The fault resets. But when a fault locks up completely, something different happens. The plates stop moving on the surface. The stress keeps building underneath. Year after year, the pressure stacks up with nowhere to go, like squeezing a spring tighter and tighter without ever letting go. Scientists call this the Cascadia subduction zone. It is one of the most dangerous fault systems on Earth, and right now, it is completely silent. That silence has lasted since January 26, 1700. That was the last time this fault fully released. Since that night, the plates have been locked, and the pressure has been growing every single day. To understand how much energy that represents, picture the entire state of Oregon being slowly compressed from both sides. Every year adds more force. Every decade multiplies it. After 3 centuries of that, the stored energy along this fault is almost impossible to picture. Scientists estimate the next full rupture could reach a magnitude of 9.0 or higher. That is roughly 30 times more powerful than the earthquake that destroyed parts of San Francisco in 1906. And the fault runs directly under one of the most populated coastlines in North America. Seattle sits above it. Portland sits above it. Dozens of coastal towns in Oregon, Washington, and Northern California sit directly in its path. Millions of people go to work, drive their kids to school, and sleep at night on ground that is slowly being compressed by forces they cannot see or feel. Here is what makes this different from most earthquake zones. Most fault lines give warning signs: small quakes, gas releases, ground deformation. Scientists can track those signals and sometimes predict increased risk. The Cascadia fault has been giving almost no surface warning at all for 300 years. The locked zone is so tightly sealed that very little energy escapes. Picture a dam holding back a lake. A healthy dam leaks a little. Water seeps through the cracks. Pressure bleeds off. And engineers can monitor the flow. A dam with no leaks looks perfect from the outside. But if the walls are quietly developing stress fractures deep inside, you would never know until the whole thing fails at once. That is the Cascadia subduction zone. Quiet on the surface, loaded underneath. Recent seismic activity along its edges has scientists watching more closely than they have in years. Small earthquakes, underground tremors, signals that suggest the plates are shifting in ways that matter. Something is changing along this fault. And to understand what comes next, you first need to understand exactly what is happening deep beneath your feet. Right now, as the Juan de Fuca plate keeps pushing, and the North American plate refuses to give way. Right now, under the Pacific Ocean, a plate of rock the size of Idaho is moving. You cannot feel it. You cannot see it. But it is moving at roughly the same speed your fingernails grow, about 2 inches per year. Over a human lifetime, that adds up to about 15 feet of movement. Over 300 years, that is close to 50 feet of pressure. that has never been released. This plate is called the Juan de Fuca Plate. It sits under the northeastern Pacific Ocean, and it has one job: slide eastward and dive beneath North America. Scientists call this process subduction, and it has been happening for millions of years. The Juan de Fuca Plate is essentially a slow-moving conveyor belt carrying ocean floor material toward the continent and then plunging it down into the hot mantle below. Under normal conditions, this process is almost graceful. The oceanic plate slides beneath the continental plate, sinks deeper, heats up, and eventually melts back into the Earth. Volcanoes like Mount Rainier and Mount St. Helens exist because of this exact process. The descending plate releases water into the mantle, which lowers the melting point of the rock above it, and magma rises to the surface. The Cascade volcanic chain is a direct product of the Juan de Fuca Plate diving underneath North America. So in a way, this plate built the Pacific Northwest, and it may also be the thing that tears it apart. Here is where the trouble starts. The boundary between the Juan de Fuca Plate and the North American Plate is not smooth. It is rough, irregular, and covered in friction. As the oceanic plate pushes eastward and tries to slide underneath, the two plates grab onto each other. They lock. The movement stops at the surface, but the force behind it keeps pushing. Think of it like trying to slide a heavy rug across a rough floor. You push, the rug catches, and instead of moving, the rug bunches up. The tension builds in the material. At some point, the grip gives way and the rug snaps forward all at once. That snap is what scientists call a megathrust earthquake. The locked portion of the Cascadia fault runs from the surface of the seafloor down to a depth of about 20 miles underground. That entire zone is frozen in place, gripping tight, storing energy. Below that depth, the plates do slide past each other slowly, but the locked section above holds everything in place like a brake. What scientists have started watching is what happens just below that locked zone. Deep tremors, slow movements, signals that the boundary between sliding and locking is active, and recent earthquakes have been occurring right at that boundary, at the exact depth where the locked section meets the slowly sliding section below. That location matters, because stress that builds in the sliding zone can transfer upward into the locked zone. Every shift below adds a little more pressure to the frozen section above. The plates are not resting. They are straining against each other every hour of every day, and the friction holding them together has a limit. When that limit breaks, the energy will not release gradually. It will release all at once, in a matter of minutes, in a wave that moves outward in every direction at the same time. And the story of what that looks like already happened once before. The date was January 26th, 1700. And the evidence of that night is still visible on the coast today. On the evening of January 26, 1700, the Pacific Northwest coastline dropped. In a matter of seconds, land that had sat safely above sea level for thousands of years sank by several feet. Entire forests along the coast went underwater. The trees did not fall. They stayed standing, roots in the ground, branches reaching upward, as the ground beneath them sank below the ocean's reach, and salt water flooded in around them. The shaking lasted for roughly 2 full minutes. 2 minutes does not sound long, but stand in a room and count to 120. During a magnitude 9.0 earthquake, every one of those seconds involves violent, relentless ground motion. Buildings collapse, roads crack open, bridges fail, people cannot stand up. Anything not bolted down becomes a projectile. When the shaking finally stopped, the coastline was permanently different. The land that sank stayed down. Forests that had lined the shore were now submerged, salt water killing the trees from the roots upward. Those trees had no defense against the ocean. They died standing up, preserved in place by the cold water and oxygen-poor sediment around their roots. Scientists today can walk along certain stretches of the Oregon and Washington coast and find the stumps still there. Some poke above the mud at low tide. Some are buried just below the surface but still detectable. These ghost forests are physical proof of what the fault did in a single night 3 centuries ago. But the shaking was only part of it. When the seafloor dropped along the fault, it displaced an enormous volume of water. The ocean floor moved, and all the water sitting above it had to go somewhere. That displacement launched a tsunami. A massive wave, or more accurately a series of waves, radiated outward from the fault in every direction. Toward the coast, the waves arrived within minutes. Anything that had survived the shaking near the shoreline faced walls of water rushing inland. Away from the coast, the waves spread westward across the open Pacific. They moved at roughly 500 miles per hour across deep water, fast enough that they crossed the entire Pacific Ocean in a matter of hours. And then they hit Japan. Villagers on the eastern coast of Japan recorded a mysterious tsunami that arrived with no local earthquake to explain it. Ships were damaged. Coastal communities flooded. The waves were real, powerful, and had traveled thousands of miles from a source that Japanese residents had no knowledge of. Those Japanese records survived, and they became one of the key pieces of evidence scientists used centuries later to piece together exactly what happened on January 26, 1700, and to calculate the magnitude of the earthquake that caused it. The 1700 event showed what this fault is capable of when it fully ruptures. The coastline changed shape overnight. The ocean reached places it had never touched in living memory, and the energy traveled so far, it caused damage on the other side of the world. That was 325 years ago. The fault has been locked and recharging ever since, but those Japanese records hold a secret that most people have never heard. The way scientists figured out the exact date of the American earthquake is a story that sounds more like detective work than geology. Nobody in the Pacific Northwest wrote down what happened on January 26, 1700. The indigenous communities who lived along that coast survived the earthquake and the tsunami, and their oral histories carry the memory of a great shaking and a great wave. But there were no European settlements in the region yet, no written records, no newspapers, no official accounts. From the American side, the date was a blank. For a long time, scientists knew a major Cascadia earthquake had occurred, but they could not pin down exactly when. They could look at the ghost forests, study the sediment layers, and examine the coastal land that had dropped, but dating those physical features precisely was difficult. The evidence pointed to sometime in the late 1600s or early 1700s, but the exact date stayed out of reach. Then scientists looked across the Pacific. Japanese coastal communities had kept meticulous written records for centuries. Village leaders documented floods, storms, and unusual wave events in detail. When researchers began combing through Japanese historical archives looking for tsunami records, they found exactly what they needed. Several villages along Japan's eastern coastline recorded a tsunami that struck on the morning of January 27, 1700, by the Japanese calendar. The waves came without any local earthquake warning. No shaking preceded them. The water simply rose and surged inland without explanation. Japanese officials at the time described it as an orphan tsunami, a wave with no local parent event. That phrase became the key. Scientists knew how fast tsunamis travel across the Pacific. They knew the approximate distance between the Cascadia Fault and the Japanese coast. Working backward from the Japanese arrival time, they calculated when the source earthquake had to have occurred. The math pointed precisely to the evening of January 26, 1700 Pacific time, along the Cascadia subduction zone. The timing matched perfectly. The magnitude needed to send waves powerful enough to reach Japan and still cause damage after crossing more than 5,000 miles of open ocean pointed to a magnitude 9 or higher. A smaller earthquake would have produced waves that lost too much energy during the crossing to cause the flooding the Japanese records described. This was detective work spread across 2 continents and 3 centuries. American geology, Japanese history, and ocean physics combined to solve a mystery that no single discipline could crack alone. And the story went even further. Researchers cross-referenced the Japanese records with tree ring data from the ghost forests on the Oregon coast. Dead trees stop growing the moment they die. By counting the rings in the submerged stumps and identifying the last ring before death, scientists confirmed those trees died in the late 1600s or very early 1700s. The Japanese records narrowed the date. The tree rings locked it in. January 26, 1700 became a confirmed date in geological history, proven by evidence gathered a century apart on opposite sides of the world. What made this finding important was not just the historical record, it was the template it created for understanding what a full Cascadia rupture actually does. Coastline subsidence. Immediate tsunami, waves powerful enough to cross the Pacific and still cause damage in Japan. The 1700 event left a physical signature that is still readable today, and some of that signature is still standing on the coast, visible at low tide, silent and strange. Those ghost forests deserve a closer look. Walk along certain stretches of the Oregon coast at low tide, and you will find something that should not be there. Tree stumps, dozens of them, some the width of a car, some barely larger than a dinner plate. They stick up through the mud and sand, dark and weathered, their roots still embedded in the ground beneath the surface. They look old. They are old. Some of these stumps are over 300 years dead. They are the remains of forests that grew on dry land, above the reach of the ocean. In the years before the 1700 earthquake, when the fault ruptured and the coastline dropped, those forests dropped with it. Salt water flooded in within hours. The trees, which had no tolerance for salt immersion, began to die. Over the following months and years, the standing timber rotted and fell, but the stumps, protected by cold water and oxygen-poor mud, were preserved. Scientists can identify these as cedar, spruce, and other coastal tree species, the same kinds that still grow in the region today. By drilling into the preserved wood and counting annual growth rings, researchers can determine exactly how old the trees were when they died and narrow down the season of death. The outermost ring on most of these stumps stopped forming in the growing season just before the 1700 earthquake, confirming that the trees died in the winter of 1699 to 1700. These forests are not just historical artifacts, they are a measuring tool. By comparing how far the stumps are now below sea level with where the original forest floor would have been, scientists can calculate how much the land dropped during the earthquake. The measurements point to a drop of roughly 3 to 6 feet along different stretches of the coast. That number is critical because it tells scientists how much energy the fault released and gives them a model for what future ruptures might do to the same land. The ghost forests also reveal something about the timing of these events. Scientists have found multiple layers of buried soil along the Oregon and Washington coast, each one containing the remains of a dead forest, each one separated from the next by centuries of sediment. These buried layers represent multiple Cascadia megaquakes over thousands of years. The fault does not rupture once and stop. It ruptures, recharges, locks again, and eventually ruptures again. The pattern suggests Cascadia experiences a full megaquake roughly every 200 to 500 years on average. The last one was 325 years ago. The fault is within the range where a rupture becomes increasingly likely. Standing near one of these stumps, you are looking at a clock, a biological record carved into dead wood that tells you what this coastline is capable of and roughly how often it happens. The next time, it will not just be forests that go underwater. Cities line this coast now. Roads, bridges, hospitals, schools. Everything built on the assumption that the ground will stay where it is. Scientists have been working to calculate exactly how far and how fast the land would drop in a future rupture, and the numbers are uncomfortable. But before getting to the modern risk, it helps to understand something most people have never tried to imagine. What does a 2-minute magnitude 9.0 earthquake actually feel like from the inside? 2 minutes of violent shaking does not sound like much until you start picturing what happens inside those 2 minutes. A magnitude 9.0 earthquake releases more energy than all the nuclear weapons ever built, detonated at the same time. That energy moves through the ground in waves, and the waves do not arrive gently. The ground does not just shake, it rolls, lurches, heaves, and snaps in multiple directions, almost simultaneously. In the first few seconds, most people would not understand what was happening. A deep, low rumble arrives before the shaking, traveling faster than the destructive waves behind it. Then the surface waves hit. The ground moves in rolling motions, like standing on the deck of a ship in a storm. Except, the ship is also shaking violently sideways at the same time. Standing upright becomes nearly impossible. Most people drop to the floor within the first 10 seconds. Furniture slides. Shelving units tip. Windows crack. The sounds are described by survivors of past megaquakes as a continuous roar, like standing next to a freight train that never passes. At 30 seconds, buildings that were not built to flex are beginning to show damage. Unreinforced brick structures develop cracks. Chimneys break. Gas lines begin to stress at their joints. Older concrete structures designed decades ago without modern earthquake standards start to fracture. At 60 seconds, the shaking has not stopped. This is the part that survivors of past major earthquakes describe as psychologically overwhelming. The human brain is wired to expect an earthquake to last 5 to 15 seconds. When the shaking continues past that point, the mind begins to process that something categorically different is happening. At 90 seconds, anything built on soft, water-saturated soil begins to experience liquefaction. This is when the ground temporarily behaves like a liquid. Sand and soil lose their structure, and objects sitting on top of them begin to sink. Roads buckle. Building foundations tilt. Underground pipes shift out of alignment. At 2 full minutes, the rupture finishes. The shaking slows. Dust fills the air, and the coast has already changed shape. The land along the fault has either risen or dropped, depending on location. Areas directly over the rupture zone could drop by several feet in a matter of seconds. The ocean floor has moved. Water displacement has already begun pushing the first tsunami waves toward the shore. For people near the coast, the clock starts the moment the shaking stops. Tsunami waves are not the slow-rolling swells most people picture. They are walls of water moving at the speed of a fast car on a highway, carrying debris, vehicles, and anything else caught in their path. Researchers estimate the first waves could reach some coastal communities in as little as 15 to 20 minutes after the earthquake ends. 2 minutes of shaking, then the ocean comes. That sequence is based on what the fault is capable of when it fully ruptures. But scientists watching recent activity along the Cascadia edge are tracking something more immediate. 2 earthquakes occurred in quick succession in recent months, and the location and timing of both raised serious questions. The first one struck off the Oregon coast. The second struck further south. And what happened right before the second one is the part that caught everyone's attention. Earlier this year, a magnitude 6.0 earthquake struck off the coast of Oregon. On most fault systems, a 6.0 is noteworthy. Seismographs light up. Scientists take a look, and if nothing unusual follows, the event gets logged and filed. But this earthquake hit in a location that made researchers pay closer attention than usual, near the Blanco fracture zone, a transform fault system that runs parallel to the southern end of the Cascadia subduction zone. The Blanco fracture zone is a separate fault from Cascadia, but it sits right at the boundary where the Juan de Fuca plate meets the Pacific plate. Earthquakes there are common. What made this one different was the timing. The Pacific Northwest had already been unusually active in the weeks surrounding this event. Scientists monitoring the region had been tracking elevated seismic signals, and the 6.0 added another data point. to a pattern that was starting to take shape. To understand why location matters so much here, picture the Cascadia fault system as a long rope pulled tight between two posts. The Blanco fracture zone sits at the southern anchor point of that rope. Stress on the anchor affects tension in the rope. An earthquake at the edge of the system can redistribute force along the fault, shifting where pressure concentrates. Scientists do not yet know whether the Oregon quake directly affected stress on the main locked fault. Stress transfer at this scale is one of the hardest things in seismology to measure with confidence. But the event placed the region under increased scrutiny. Monitoring networks along the Pacific Northwest coast and offshore use sensors called seismometers, hydrophones, and seafloor pressure gauges to detect motion in the water and the crust. After the Oregon quake, scientists increased their review frequency on these networks, looking for any follow-up signals that might suggest the stress had moved somewhere unexpected. What they were watching for specifically was activity near the locked zone. The 6.0 was in the fracture zone, not directly on the main thrust fault. But the history of large subduction zone events around the world shows that elevated activity near the edges of a locked system sometimes precedes larger changes on the main fault. That word sometimes carries a great deal of weight. Seismology is not a precise prediction science. Scientists cannot look at a 6.0 earthquake off the Oregon coast and say with confidence that a megaquake is coming. What they can say is that a system under extreme stress showed a measurable signal, and that signal deserves monitoring. Then, shortly after the Oregon event, something else happened further south. An earthquake struck offshore Northern California. It was smaller than the Oregon quake, only a magnitude 4.8. Under normal circumstances, that would not make headlines. But the timing of that earthquake, measured in minutes against an event happening on the other side of the continent, was the kind of coincidence that scientists do not easily dismiss. On a morning in early 2026, a magnitude 4.8 earthquake struck offshore Northern California. A 4.8 is small. Most people would not feel it strongly. It would register on instruments, get logged in the database, and likely draw no public attention at all. Except for one detail that made seismologists stop and look twice. Just minutes before the California quake hit, a separate earthquake had fired off thousands of miles away in the Aleutian Arc, near Alaska. Two earthquakes, two completely different tectonic systems, separated by thousands of miles, happening minutes apart. Scientists generally expect earthquakes on different fault systems to be independent events. The Earth is large. Faults are separated by enormous distances. The idea that stress from one earthquake could travel thousands of miles and trigger a second earthquake on a separate fault within minutes goes against the simple model most people learn in school. But research over the past 2 decades has complicated that simple model. Scientists studying large earthquake networks have documented cases where a major rupture on one fault sends seismic waves traveling across the planet, and those waves pass through other fault systems in ways that can temporarily change the stress conditions on those faults. This process is called dynamic stress triggering, and it remains one of the more debated topics in earthquake science. The California and Aleutian events have not been formally confirmed as linked. Researchers are cautious about drawing direct connections without rigorous analysis. The timing could be coincidence. Earthquake databases record thousands of events per day globally, and occasional coincidences in timing are statistically expected. What made scientists look more carefully was the specific location of the California quake. It struck offshore in an area that sits directly above the southern section of the Cascadia subduction zone, and it struck during an active slow slip event that was already in progress in that region. Slow slip events are underground movements that happen without producing felt earthquakes. The plates shift slightly at depth, instruments detect the faint signals, and the ground above stays calm. These events repeat on roughly seasonal cycles along the Cascadia fault. They are considered a normal part of the fault system's behavior. Having a felt earthquake land in the middle of an active slow slip cycle is less common. Having that felt earthquake arrive minutes after a distant event in Alaska, in a region already under elevated stress, monitoring created a cluster of signals that researchers found worth examining carefully. The 4.8 was a small earthquake, but it landed in exactly the wrong place at exactly the wrong time to be ignored. And it was directly connected to a deep underground process that scientists have been tracking along Cascadia for years, one that moves silently and shifts stress in ways that cannot be felt on the surface. That process has a name, and understanding it changes how you think about what is building beneath the Pacific Northwest. Deep underground, right now the Earth is moving without making a sound. No shaking, no rumbling, no warning on your phone. The ground beneath your feet stays perfectly still. But at a depth of about 15 to 25 miles below the surface, two massive plates are slowly grinding past each other in a movement so gradual it takes weeks to complete. Scientists call this process episodic tremor and slip. The tremor part is real seismic activity, faint vibrations that instruments can detect. The slip part is actual plate movement, where the boundary between two tectonic plates shifts by small amounts over days or weeks. But because the slip happens so slowly and so deep, the energy never builds up fast enough to produce felt earthquakes. To picture what this looks like, imagine a zipper. The locked portion of the Cascadia fault is like a zipper that is completely closed, held shut by enormous friction. Below the locked zone, the plates slide past each other. During an episodic tremor and slip event, the deep section of the fault creeps forward slightly, like a slow, invisible hand moving along the bottom of the zipper. The surface above stays still, but the pressure distribution inside the fault shifts. These events repeat on a fairly predictable cycle along the Cascadia subduction zone. In many sections of the fault, slow slip events occur roughly every 12 to 15 months. Scientists have been monitoring them for years using GPS sensors planted across the Pacific Northwest. During a slow slip event, the sensors detect the land moving westward by fractions of an inch, then returning as the deep plates shift below. What researchers are most interested in is the relationship between these slow slip events and the locked zone sitting just above them. The slow slip zone and the locked zone share a boundary. When the slow slip zone creeps forward, it changes the stress conditions at the bottom edge of the locked zone. Think of the locked zone as a wall holding back enormous pressure. The slow slip movement happening below is like someone quietly tapping on the bottom of that wall. Each tap alone means nothing, but over many cycles those taps accumulate. The stress at the base of the locked zone grows slightly after each slow slip event. Scientists disagree about how significant this effect actually is. Some researchers believe slow slip events genuinely increase the probability of a major rupture in the locked zone above. Others think the effect is too small to meaningfully change the timeline. What is agreed upon is this: the slow slip events are real, they are measurable, and they are ongoing. And the recent magnitude 4.8 earthquake in Northern California happened at the exact time and location of an active slow slip cycle. That is not something scientists expected to see. A felt earthquake landing inside a slow slip event in the middle of the Cascadia system raised a specific and uncomfortable question. What happens when a felt earthquake and a slow slip event combine their stress in the same place at the same time? And does that combination move stress upward into the locked zone above? The answer is still being studied, but what researchers already know about how stress transfers through this fault makes the question harder to ignore. The magnitude 4.8 earthquake off Northern California did not strike randomly. It struck at the precise moment when a slow slip event was actively moving through that section of the Cascadia fault. Scientists confirmed the alignment after analyzing data from both the earthquake sensors and the GPS networks that track slow slip activity. The two events were happening simultaneously in the same region at overlapping depths. This matters because of how stress moves through rock. A slow slip event creates a zone of change stress at the base of the locked fault. Within that zone, the rock is in a slightly different state than it was before the slip began, with pressure redistributed along the fault boundary. A small earthquake hitting that same zone during an active slip cycle encounters rock that is already stressed in specific ways. Scientists studying other subduction zones around the world have documented cases where small earthquakes cluster along the edges of active slow slip zones. The theory is that the slow slip changes stress conditions just enough to bring nearby rock closer to its failure threshold. A small push from a passing earthquake can then trigger motion in rock that was already near its limit. In the Northern California case, the 4.8 was likely not triggered by the slow slip alone. The fault in that area sits within a broader zone of tectonic activity near the southern end of the Cascadia system, where multiple fault structures intersect. The Aleutian earthquake that struck minutes earlier may have sent seismic waves through that region, temporarily altering stress conditions there too. What scientists are still working to understand is whether the combination of signals, the slow slip event, the small earthquake, and the distant Aleutian event, represents a meaningful change in stress on the locked Cascadia fault above. The locked fault sits above the slow slip zone. It is roughly 15 to 20 miles shallower than where the slow slip activity occurs. Stress does not jump instantly between those depths, but over time, and over multiple slow slip cycles, the cumulative effect of stress transfer from the deep zone upward into the locked zone is real and measurable. Researchers at universities across the Pacific Northwest have been building models to simulate this process. They feed in data from GPS sensors, seismometers, and offshore pressure gauges to track how stress is distributed across the entire fault system. The models do not predict earthquakes. What they do is help scientists understand which parts of the fault are accumulating stress fastest and which areas are closest to their failure threshold. Those models have consistently pointed to the same result. The locked Cascadia fault has been accumulating stress steadily since 1700. Every slow slip cycle adds a small increment to that total. Every decade that passes without a rupture means more stored energy. The recent alignment of a slow slip event with a felt earthquake in the same region is a data point, one piece of a much larger puzzle. Researchers are careful not to overstate its significance, but they are also careful not to dismiss it, because the next piece of the puzzle, the one that explains how the locked fault actually fails, involves a concept that changes the way you think about what is frozen beneath the Pacific Northwest. Stress does not stay where it starts. When one part of a fault slips, even slightly, the rock around it adjusts. Pressure that was sitting in one spot moves. Some of it bleeds off. Some of it transfers sideways or upward into adjacent sections of fault. This invisible redistribution of force is called stress transfer, and it happens constantly along every major fault system on Earth. The reason scientists pay such close attention to it along Cascadia is because the geometry of the fault makes stress transfer particularly significant here. The Cascadia subduction zone has two distinct behavior zones stacked on top of each other. The locked zone sits closer to the surface, roughly from the seafloor down to about 15 miles deep. Below that, the transition zone is where the plates begin to slowly creep and where episodic tremor and slip events occur. Every time a slow slip event moves through the transition zone, it alters the stress distribution at the base of the locked zone above it. Imagine pressing your thumb into a balloon from below. The skin of the balloon directly above your thumb stretches tighter. You have not popped the balloon, you have changed the stress distribution in the material directly above the pressure point. Scientists call the relevant force here Coulomb stress. It measures how close a section of rock is to failing, to slipping suddenly and generating an earthquake. When Coulomb stress increases in a section of the locked fault, that section moves closer to its failure threshold. Slow slip events repeatedly load small amounts of Coulomb stress into the bottom edge of the locked zone. Each individual cycle loads a tiny amount, but 300 years of cycles occurring every 12 to 15 months adds up to a significant cumulative transfer. Some researchers have tried to calculate whether this cumulative transfer is enough to meaningfully shorten the time before the locked zone ruptures. The results are not definitive, but they are consistent. Slow slip events do appear to contribute to stress loading on the locked fault, and that contribution is real even if its magnitude is uncertain. What makes the recent signals more interesting is the spatial alignment. The magnitude 4.8 earthquake in Northern California struck in a section of the fault where the slow slip zone and the locked zone sit particularly close together in depth. That geometry means stress transfer between the two zones happens over a shorter distance and potentially with greater efficiency. The combination of a slow slip event, a felt earthquake in the transition zone, and the proximity of those signals to the locked fault above created a cluster of readings that scientists are analyzing carefully. None of this proves a megaquake is imminent. Seismology has no tool that can make that determination. What these signals do is confirm that the fault system is actively loaded and that stress is moving within it in ways consistent with a fault approaching a long-term rupture cycle. And the fault has been approaching that cycle for a very specific reason, one that becomes clear when you understand what it means for a fault to be locked for over 3 centuries. A fault that never breaks is a fault that never rests. Most people assume that a quiet fault is a safe fault. The logic seems reasonable. No earthquakes means no danger. But in the world of subduction zones, the opposite is true. A fault that produces small earthquakes regularly is releasing stress in manageable amounts. A fault that stays completely locked is storing all of that stress, compressing it into the rock, building a debt of energy that grows larger with every year that passes. The Cascadia subduction zone has been locked since January 26, 1700. That is over 325 years of continuous pressure accumulation. To understand what that means in physical terms, consider what the Juan de Fuca plate has been doing during those 3 centuries. It has moved approximately 2 inches per year, consistently without stopping. The plate does not know the fault is locked, it just keeps pushing. Over 325 years, that adds up to roughly 54 feet of plate movement that has never been accommodated at the surface. That 54 feet of movement is stored as elastic strain in the rock. The crust above the locked fault has been slowly deforming, bending, compressing, building up like a coiled spring that is wound tighter every year. When the fault finally ruptures, that stored strain releases in seconds. The rock that was bent snaps back. The land that was compressed lunges forward. The seafloor that was pulled down heaves upward. All of it happening at once, driven by 54 feet worth of accumulated plate motion releasing in a matter of minutes. This is what scientists mean when they say the Cascadia fault is capable of a magnitude 9 or greater. The magnitude is a measure of the total energy released. 300 years of strain accumulation along a fault 400 miles long produces energy on a scale that is genuinely difficult to compare to anything in everyday experience. The historical record from past Cascadia events suggests the fault ruptures on a cycle of roughly 200 to 500 years. 325 years puts the current interval within that range. The fault is not overdue in a strict scientific sense because earthquake timing cannot be predicted precisely, but it is within the window where the probability of rupture is elevated and climbing. Scientists have calculated a 37% probability of a magnitude 7.1 or larger earthquake on this fault within the next 50 years. A full magnitude 9 rupture is considered a lower probability event within that window, but the probability is real and growing. That number, 37% in 50 years, sounds abstract until you frame it differently. A 1 in 3 chance of a catastrophic earthquake during your lifetime in a region where millions of people live, work, and go to school, and when the fault finally does release, the first visible consequence will not be shaking. It will be the ground itself changing shape faster than any human can react. The coast will drop permanently in seconds. Scientists do not like saying an earthquake is coming. The history of earthquake prediction is full of false alarms, missed events, and public panic that caused more harm than the predicted quakes ever did. So when researchers calculate a 37% probability of a major Cascadia earthquake within 50 years, they choose those words carefully. 37% means that if you could run the next 50 years, over and over again, like replaying a video game from the same save point, a magnitude 7.1 or larger earthquake on the Cascadia fault would happen in roughly 1 out of every 3 playthroughs. For comparison, seismologists consider a 10% probability of a damaging earthquake in 50 years to be enough to justify major infrastructure investment and emergency planning requirements. The Cascadia fault sits at more than 3 times that threshold. The probability is calculated from multiple data sources. Geological records of past ruptures preserved in sediment layers and ghost forests along the coast show how often the fault has ruptured over thousands of years. GPS measurements show how fast strain is accumulating today. Slow slip event cycles show how frequently stress is being added to the locked zone. Each of these inputs feeds into a model that produces the probability estimate. The 37% figure covers earthquakes of magnitude 7.1 or larger. A full Cascadia megaquake, the kind that ruptures the entire 400-mile fault at once, carries a lower probability within that same 50-year window, roughly 10 to 15% by some estimates. That number sounds smaller, but 10 to 15% in 50 years for an event that could affect millions of people and reshape the Pacific Northwest coastline is a probability that emergency planners take extremely seriously. What makes the probability conversation difficult is the uncertainty range. Scientists are confident in the general framework, that the fault is loaded, that it will rupture, and that the probability is elevated. But the specific number could be higher or lower depending on assumptions about past rupture intervals, which are themselves estimated from incomplete geological records. The honest answer from seismologists is this: the fault will rupture. When is unknown. The probability within any given decade is real but not dominant. The probability within a century is high enough that preparing for it is rational and urgent. For the people living along the coast, the probability conversation leads to a practical question. When the fault does rupture, what exactly happens to the ground they are standing on? The answer to that question is one of the more disturbing findings from recent research, because the shaking is only the first part. The second part happens immediately after, and it changes the geography of the coast permanently and instantly. The shaking stops. And then the coast changes shape. During a full Cascadia rupture, the land above the fault does not stay where it is. The crust that has been bending under centuries of strain snaps back into a new position. Some areas rise, some areas drop. Along much of the Pacific Northwest coastline, the land is expected to subside, meaning it will sink by up to 6 feet in a matter of seconds. 6 feet does not sound catastrophic until you picture what it means for a neighborhood that currently sits 4 feet above sea level. Communities along the Oregon and Washington coast are built on coastal plains that range from a few feet to a few dozen feet above the current ocean line. Many of the most densely populated areas, the ones closest to fishing harbors, beaches, and commercial waterways, sit on low ground. After a rupture, some of that low ground would be permanently below sea level. The mechanism behind this subsidence is the same elastic strain that has been building for 3 centuries. The Juan de Fuca plate has been slowly dragging the edge of the North American continent downward as it pushes underneath. The locked fault holds the surface from snapping back. When the fault releases, the surface rebounds, but the rebound is not uniform. Directly above the rupture zone, the seafloor can rise sharply, but the coastal land further inland, which was being pulled and bent in the other direction, drops. We have measured this effect at past Cascadia events using the ghost forests as reference points. The depth of the drowned stumps below current sea level gives them a direct measurement of how far the land dropped in 1700. Those measurements show drops ranging from roughly 3 to 6 feet across different sections of the coast. A future rupture is expected to produce similar subsidence, possibly more severe in some areas, because strain accumulation has continued for over 300 years. The drop happens fast. Survivors of the 2004 Indian Ocean earthquake, which involved a similar subduction fault, reported that coastal areas near the fault changed elevation almost instantly when the rupture reached them. The ground simply fell. Roads that had been above water were suddenly submerged. Structures that had been on dry land were standing in the ocean. For Cascadia, this immediate subsidence creates a secondary problem that compounds the tsunami threat. Coastal communities that drop by several feet lose their elevation buffer. Areas that might have been just out of reach of incoming tsunami waves are now lower, and the same waves reach further inland. The land does not bounce back after the event. The new elevation is the new reality for years or decades, until geological processes very slowly reshape the coast. That permanence makes the subsidence different from the shaking. The shaking ends. The land drop does not. And when you combine that permanent drop with a separate factor that has been building slowly for decades, the long-term flood exposure along this coast multiplies in a way that researchers are only now fully mapping. The moment the fault ruptures, some neighborhoods along the Pacific Northwest coast will enter a permanent flood zone. Researchers studying the combined effects of earthquake subsidence and existing land elevation have mapped which communities face the highest risk of immediate and lasting inundation after a Cascadia megaquake. The results are sobering. Coastal towns built on river deltas, estuary floodplains, and low-lying beach plains face the highest exposure. These are often the same areas with the highest population density along the coast, because flat, low ground near water is historically where fishing towns, ports, and commercial centers develop. The very features that made these locations attractive for settlement are the features that make them most vulnerable to permanent flooding after subsidence. In a worst-case rupture scenario, scientists estimate that some sections of the Oregon and Washington coast could experience land drops large enough to permanently submerge roads, sewage systems, and building foundations. Emergency planners in Oregon have been working with these models to identify which evacuation routes would remain passable after a major rupture, and which would be underwater before the tsunami even arrives. The situation is more complicated than simple flooding. Infrastructure built at current elevations was designed and installed based on those elevations. Water and sewer pipes have specific slopes that allow gravity to move flow in the right direction. When the ground drops by several feet, those slopes change. Gravity-fed systems stop working. Groundwater intrusion into basements and foundations begins immediately. Saltwater, which corrodes metal and concrete faster than fresh water, starts attacking buried infrastructure from below. Recovery from this kind of damage takes years, not weeks. After the 2004 Indian Ocean tsunami, coastal communities that experienced subsidence faced infrastructure challenges that lasted for more than a decade, even in areas where the physical tsunami damage was not catastrophic. For Pacific Northwest communities, the combination of a major tsunami and permanent subsidence creates a recovery timeline that emergency planners describe as one of the most complex in North American disaster history. And the subsidence problem does not stop at the earthquake itself. A separate, slower process has been building alongside it for decades, one driven by rising ocean temperatures and melting ice. When that process is added to the subsidence projection, the long-term flood exposure numbers change dramatically. Scientists at one university ran the calculation. They looked at projected sea level rise from climate change combined with the subsidence expected from a Cascadia rupture, then mapped how many properties currently above flood risk would fall inside the flood zone by the year 2100. The result was a number that changed how coastal planners in Oregon and Washington think about land use, zoning, and long-term development along this coastline. The flood exposure could triple. Two processes are pushing the Pacific Northwest coast toward the same outcome from different directions. One is sudden, One is gradual. Together they create a flood risk by the year 2100, that is, 3 times larger than what current maps show. The sudden process is the earthquake subsidence described earlier. A full Cascadia rupture drops coastal land by up to 6 feet in seconds. That new, lower elevation becomes the permanent baseline. The gradual process is sea level rise. Global ocean levels have been climbing as ice sheets melt and warming water expands. Projections for sea level rise along the Pacific Northwest coast vary, but estimates for the end of this century range from roughly 1 to 3 feet of additional ocean height, depending on how much global emissions are reduced. When both processes happen, the math compounds. A neighborhood that currently sits 6 feet above sea level might experience 3 feet of subsidence from the earthquake and 2 feet of sea level rise over the following decades. That leaves it 1 foot above the ocean, instead of the 6 feet of safety it has today. Researchers studying this combined effect examined coastal flood exposure along Oregon and Washington. They mapped current flood zones, then layered in projected earthquake subsidence and sea level rise, and calculated how many additional properties would fall inside the 100-year flood zone by 2100. The study found that the combined effect could place roughly 3 times as many properties at serious flood risk as current flood maps indicate. Communities that have never required flood insurance, never needed elevated foundations, and never been included in emergency flood planning could find themselves inside permanent flood zones within the lifetimes of people alive today. This creates a planning problem that has no simple solution. Building codes and zoning regulations along the Pacific Northwest coast are based on current flood maps. Flood insurance requirements follow those maps. Infrastructure investments use those maps to determine which roads, bridges, and utilities need flood hardening. If the maps are wrong by a factor of 3, a significant portion of the investment and planning is inadequate. Some coastal counties in Oregon and Washington have begun updating their planning documents to account for this combined risk. Others are still using pre-earthquake, pre-climate rise projections. The gap between current planning assumptions and what the science projects is one of the clearest examples of infrastructure unpreparedness along this coastline. The triple threat calculation also changes the economics of coastal property. Homes and businesses that currently sit outside flood zones carry different insurance requirements, different financing terms, and different resale values than properties inside flood zones. If the zone expands dramatically after a rupture, the financial consequences for coastal property owners compound on top of the physical damage from the earthquake and tsunami. But the flood risk from subsidence and sea level rise, as severe as it is, affects coastal areas primarily. Move inland to the cities to Seattle and Portland, and a completely different earthquake risk takes over. One that has nothing to do with the ocean, and everything to do with what is underneath the streets. Seattle and Portland sit on ground that will betray them during an earthquake. Both cities were built over deep basins filled with soft sediment, the kind of loose, water-saturated material that was deposited by glaciers and rivers over thousands of years. Under normal conditions, this sediment feels like solid ground. You can build on it, drive on it, and walk on it without noticing anything unusual. During a major earthquake, that sediment behaves completely differently. When seismic waves move through hard bedrock, they travel fast and pass through relatively quickly. When those same waves enter soft sediment, they slow down. As the waves compress into slower moving material, they grow taller and more intense, the same way an ocean wave grows as it enters shallow water near shore. The sediment traps the wave energy and forces it to bounce back and forth within the basin. Structural engineers call this the bowl of jello effect. Imagine filling a bowl with jello and tapping the side. The whole bowl shakes. The jello amplifies the motion, shaking longer and harder than the initial tap would suggest. Seattle and Portland are the bowls. The sediment is the jello, and a magnitude 9.0 Cascadia earthquake is a very hard tap. Studies estimate that the soft sediment basins beneath Seattle and Portland could amplify seismic shaking by a factor of 2 to 3 times compared to what solid bedrock would experience. A building on bedrock during the earthquake might experience one level of shaking. A building on the sediment basin in downtown Seattle might experience 2 to 3 times that force for a longer duration. The combination of higher amplitude shaking and longer duration puts modern tall buildings under stress they were rarely designed to handle simultaneously. Engineers in the Pacific Northwest have been studying this problem since at least the 1990s, but the full extent of the basin amplification effect has only become clearer with more recent modeling. The finding that came from this research was alarming. Modern tall buildings in Seattle and Portland, structures built to current earthquake codes, face a 20% probability of collapse during a full Cascadia megaquake. 1 in 5. These are buildings with elevators, sprinkler systems, and engineering reviews. They are considered safe under normal conditions. Under Cascadia conditions, 1 in 5 may not stand. Older buildings, built before modern seismic codes were updated to reflect Cascadia risks, face significantly higher collapse probabilities. Unreinforced masonry buildings, common in older commercial districts of both cities, are considered among the most vulnerable structures in the region. The sediment problem also affects something people rarely consider: the duration of hospital operation after a disaster. Hospitals in Seattle and Portland that survive the initial shaking will be operating in buildings on sediment basins that may have experienced significant structural stress. Medical equipment may have shifted. Backup power systems may have failed. And the same sediment that amplified the earthquake shaking may have liquefied in certain areas, making road access to those hospitals impossible. Scientists have been warning about the bowl of jello effect for years. The challenge is that fixing it requires either moving entire cities or replacing their foundations, neither of which is a realistic option. What remains is understanding the risk clearly, building as well as possible within the constraints, and planning for the aftermath. And the aftermath of a Cascadia megaquake includes something even the best prepared cities were not fully expecting, until scientists began revising a long-held assumption about the tsunami. 1 in 5 modern tall buildings in Seattle and Portland may not survive a full Cascadia rupture. That number comes from structural engineering studies that model how the basin amplification effect interacts with building design under prolonged high-intensity shaking. It is not a fringe estimate. It comes from researchers at major universities and has been presented at engineering conferences, cited in government planning documents, and used by city emergency managers to shape disaster response frameworks. The 20% figure applies specifically to modern buildings, structures built under current seismic codes. The reasoning is not that modern buildings are poorly designed. They are well designed for the earthquakes this region has historically experienced. The problem is that the full Cascadia scenario, a magnitude 9 rupture with 2 minutes of shaking, amplified by soft sediment basins, exceeds the design assumptions built into many of those structures. Seismic building codes are written based on expected shaking intensity in a given region. For decades, the codes applied in Seattle and Portland were calibrated for smaller, more local earthquakes. The Cascadia subduction zone was understood to be dangerous, but the full scope of a magnitude 9 event, combined with basin amplification, was not fully incorporated into code requirements until relatively recently. Many existing buildings were designed and constructed before those updated requirements took effect. Tall buildings face a specific challenge in long-duration shaking. They are designed to sway, absorbing earthquake energy through controlled movement rather than rigid resistance. During a 10-second earthquake, that sway is manageable. During 2 minutes of sustained shaking, the cumulative stress on structural connections, floor diaphragms, and core walls multiplies in ways that short-duration design tests do not fully capture. The buildings most at risk are concentrated in the downtown cores of both cities, where the sediment basins are deepest and the building stock is oldest. A significant portion of Seattle's downtown commercial district sits over a sediment layer several hundred feet deep in places. far deeper than the surrounding hillsides where bedrock is closer to the surface. Emergency planners in both cities have been working on what a 20% collapse rate in the urban core would mean for first responders. The answer is stark. A simultaneous collapse of 1 in 5 tall buildings in downtown Seattle during a working day would generate a mass casualty event that overwhelms every hospital, fire station, and search and rescue team in the region. The hospital problem is particularly acute. Many major hospitals in both cities sit on sediment. They face the same amplification risk as commercial buildings, but carry the additional burden of needing to function immediately after the event, precisely when the demand for medical care would be highest and the structural condition of the buildings would be most uncertain. City engineers have been retrofitting some older structures, prioritizing schools, fire stations, and critical infrastructure. The pace of retrofitting has been slower than the urgency of the risk would suggest, constrained by funding, political will, and the sheer scale of the problem. The 20% collapse probability is the number that lives at the intersection of geology and engineering, and it sits directly below a separate question, one that scientists spent decades getting wrong, about what the ocean will do when the fault finally breaks. For years, the official tsunami projection for a Cascadia megaquake included waves reaching 100 feet high along parts of the Oregon and Washington coast. 100 feet is roughly the height of a 10-story building. Picture standing at the base of a 10-story building and watching a wall of water moving toward you at highway speed, carrying boats, cars, and entire houses in its current. That was the model. That was what emergency planners built their evacuation zones around. That was what the warning signs along Pacific Northwest coastal highways were referencing when they pointed uphill. The 100-foot projection was not invented. It was based on a specific geological feature that scientists believed existed along the length of the Cascadia Fault, a structure called a megasplay fault. A megasplay fault is a secondary fault that branches off the main subduction zone at a shallow angle and runs close to the seafloor surface near the shore. When a megaquake ruptures the main fault, the rupture can also propagate along the megasplay. Because the megasplay sits at a shallower depth and closer to the coast, its movement lifts a large section of seafloor rapidly, pushing an enormous volume of water upward in a very short time. That rapid shallow uplift is what produces the tallest and fastest arriving tsunami waves. The megasplay fault model predicted that a continuous splay fault ran along the entire length of the Cascadia subduction zone. If that were true, a full rupture of the main fault would simultaneously trigger the splay, launching massive waves toward the coast from multiple points along the 400-mile fault. Emergency planners designed evacuation maps, built vertical evacuation towers, and allocated resources based on wave heights derived from this model. Communities invested in infrastructure at specific elevations based on projections that assumed the megasplay fault was real, continuous, and active. Then scientists went looking for it in more detail. Better seafloor mapping technology deployed in recent years allowed researchers to examine the structure of the Cascadia fault zone at much higher resolution than was previously possible. What they found complicated the megasplay model significantly. The story of what that new evidence actually showed and what it means for the wave projections that coastal communities have been planning around for decades is one of the more consequential scientific revisions in Pacific Northwest earthquake research. Some communities may have been over-preparing for waves in certain areas. Others may have been under-preparing in ways they do not yet realize. The megasplay fault does not run the full length of the Cascadia subduction zone. New geological surveys using high-resolution seafloor mapping showed that the splay fault structure is present in some sections of the Cascadia zone, but absent or poorly developed in others. The assumption of a continuous megasplay running from Vancouver Island to Northern California, an assumption baked into decades of tsunami modeling, was wrong. This finding changes the tsunami picture significantly, but the change is not uniform. It does not simply make the threat smaller everywhere. It makes the threat different in different places in ways that require new, location-specific models rather than a single regional projection. In sections of the fault where the megasplay is absent or weak, the tsunami waves generated by a rupture would come primarily from movement along the main fault itself, which sits deeper and further offshore. Waves from that source would be powerful, but would arrive somewhat later and potentially with lower peak heights than the old splay-based models predicted. In sections where the splay structure is more developed, the wave projections remain closer to the original estimates. Those areas still face serious tsunami risk from a shallow fault structure capable of rapid seafloor uplift. The practical consequence is that some coastal communities were building evacuation infrastructure based on wave heights that may have been overestimated for their specific location. Vertical evacuation towers built to survive a 90-foot wave may be more than adequate protection for an area now expected to face a 50-foot wave. That is good news for those communities, though the word adequate should be used carefully when discussing any wave taller than a 5-story building. The harder conversation involves communities that may have been under planning because they were in areas where the splay fault was assumed but now known to be absent, leading planners to assume lower tsunami risk, when in reality, the wave dynamics in those areas were simply different rather than safer. Scientists working on the revised tsunami models emphasize that the update does not reduce the overall severity of the Cascadia threat. A magnitude 9 rupture along the full 400-mile fault will still displace an enormous volume of ocean water. Waves will still reach the coast. Communities in low-lying areas still need to evacuate immediately. The revision changes specific height projections in specific locations, but the fundamental danger of a Cascadia tsunami remains severe. Emergency managers in Oregon and Washington have begun reviewing their evacuation zone maps in light of the new seafloor data. That review process is ongoing. Some maps have been updated, others are still being revised. The megasplay discovery is a reminder that the science of this fault is still developing. Researchers are still learning the precise structure of the Cascadia system, and what they learn changes the projections that communities rely on to plan their survival. The fault held another surprise from history that most people have never heard about. A 1954 earthquake in California that confused scientists for decades turned out to be a direct message from the Cascadia fault, one that went unread for more than 70 years. In 1954, a magnitude 6.5 earthquake struck near Humboldt Bay in Northern California. Scientists at the time logged it, studied it, and moved on. The region had seen earthquakes before. The event caused damage, drew attention, and then faded from the primary research focus as scientists turned to other seismic events along the well-studied San Andreas fault system further south. For decades, the 1954 Humboldt Bay earthquake sat in the database as a known event with a somewhat uncertain source. The precise fault responsible for generating it was debated. The region is tectonically complex, with several fault systems converging near the southern end of the Cascadia subduction zone. Attributing a mid-sized earthquake to a specific fault in that tangle of geology is genuinely difficult. Then, in recent years, a team of researchers went back to reanalyze the historical seismic data from 1954, using modern tools and updated fault models. What they found reframed the earthquake entirely. The 1954 event, which had been loosely categorized as a local fault earthquake, was actually a rupture on the Cascadia subduction interface itself. The earthquake had originated not on a small regional fault, but on the main locked boundary between the Juan de Fuca plate and the North American plate, the same boundary capable of producing a magnitude 9 megaquake. This matters for several reasons. First, it confirmed that the Cascadia interface is capable of producing moderate earthquakes in its southern section, not just catastrophic megaquakes. This adds a category of mid-range seismic risk to the region that was not fully appreciated before. Second, it revealed that the southern end of the Cascadia fault near the Oregon-California border has been more recently active than previously understood. An interface earthquake in 1954 means the southern section of Cascadia generated a felt rupture within living memory, within the lifetimes of people who are still alive today. Third, it demonstrated that the historical earthquake record for Cascadia is incomplete. If a magnitude 6.5 interface earthquake from 1954 was only recently identified as a Cascadia event, there are likely other historical earthquakes in the catalogue that have been misattributed to smaller local faults. The real activity history of the Cascadia fault may be richer and potentially more concerning than the record currently shows. The reanalysis was made possible by improvements in seismic modelling software and a much better understanding of the three-dimensional structure of the Cascadia fault system. Researchers can now run historical earthquake data through modern fault geometry models and identify which fault a historical event most likely originated on, even decades after the fact. The 1954 discovery was one piece of a broader improvement in how scientists monitor the Cascadia system in real time, because while historians were reanalyzing old records, engineers were busy installing something on the ocean floor that changed earthquake detection entirely. 20 years ago, scientists studying the Cascadia fault were essentially working blind. They had seismometers on land, spread across the Pacific Northwest, measuring ground motion when earthquakes occurred. Those instruments were good at detecting moderate and large earthquakes. They were poor at detecting the faint, deep signals produced by slow slip events and tiny tremors happening far offshore, beneath miles of ocean water. On a fault that sits on the seafloor, the ocean hid the fault's behavior. Land-based instruments caught what reached the coast. Everything happening on the offshore section of the fault, the section that matters most for tsunami generation, was largely invisible. Then scientists began installing offshore instrumentation networks directly on the seafloor. The Ocean Observatory's initiative deployed a network of instruments along the seafloor of the Pacific Northwest coast, including seismometers, hydrophones that detect underwater sound waves, and pressure sensors that can measure the tiny vertical movements of the ocean floor caused by deep tectonic activity. These instruments sit on the seafloor directly above the locked section of the Cascadia fault and transmit data in real time through fiber optic cables connected to shore stations. The difference in detection capability was immediate and dramatic. Once the seafloor network was active, scientists began observing signals from the Cascadia fault that had been completely invisible before. Tremors so faint they would never register on a land-based instrument. Slow slip events occurring on the offshore section of the fault that could only be detected by instruments positioned directly above them. Tiny ground movements measuring fractions of an inch. The data from these networks revealed that the Cascadia fault is far more active between major earthquakes than the land-based records suggested. The locked zone is not entirely static. It produces constant, low-level signals, tremors, and creep events that paint a picture of a fault under continuous internal stress. The seafloor instruments also improved the accuracy of earthquake location measurements dramatically. When a small earthquake occurs offshore, land-based instruments can detect it, but calculating the precise depth and location requires triangulating signals from multiple distant stations, introducing uncertainty. A seafloor instrument sitting directly above the event can pinpoint the source with much greater precision. That precision matters for understanding where the fault is most stressed and which sections are accumulating energy fastest. The combination of GPS sensors on land detecting surface deformation and seafloor instruments detecting deep activity gives scientists a three-dimensional picture of the fault that was simply not possible 2 decades ago. The recent signals from the fault, the slow slip cycles, the small earthquakes, the offshore tremors, are all being captured by this network in detail that researchers are still learning to fully interpret. The instruments are generating more data than the field has ever had to analyze, and that volume of data feeds directly into the question that matters most for the people living above this fault. How much warning would they actually get if the megaquake started right now? Scientists agree the Cascadia fault will rupture, They disagree about how. The disagreement centers on a question that sounds technical but carries enormous consequences for millions of people. Will the entire 400-mile fault break at once, or will it break in separate segments at different times? A full rupture scenario means the entire locked zone, from Vancouver Island to Northern California, fails simultaneously in a single continuous event. The magnitude reaches 9 or above, 2 minutes of shaking, the full coast drops, a tsunami launches from the entire length of the fault at the same moment. A segmented rupture scenario means the fault breaks in sections, with one portion rupturing in one event, and other portions rupturing in separate smaller earthquakes at different times. Each individual rupture would be less powerful than a full rupture. The shaking would be shorter. The tsunami would be generated from a shopping section of fault and would produce smaller waves. The geological record shows evidence for both types of events in Cascadia's past. Some historical ruptures appear to have involved the full fault length. Others appear to have been partial, affecting only the northern or southern sections of the zone. The evidence is preserved in the sediment layers and ghost forests along the coast. But reading that evidence precisely enough to determine exactly which sections moved in which events requires detective work that is still ongoing. The distinction matters enormously for the cities along the fault. A full rupture puts Seattle, Portland, and every coastal town from British Columbia to California under maximum threat simultaneously. A segmented rupture might spare some areas entirely while devastating others. For emergency planning, the full rupture scenario is generally used as the design basis, because it represents the worst case. But researchers debating the segmentation question are not simply arguing about disaster movie scenarios. The answer affects how scientists interpret current signals from the fault. If the fault tends to rupture in segments, then elevated seismic activity in the southern section near Northern California and Oregon might represent stress building toward a southern segment rupture, a serious but more localized event. If the fault tends to rupture all at once, the same signals might be early indicators of stress throughout the full system. The debate has not been resolved. Both possibilities remain scientifically legitimate. What the debate reveals is that even the most fundamental question about how this fault behaves is still being answered, and the answer, when it comes, will not arrive in a scientific paper or a conference presentation. It will arrive as ground motion detected first by the Seafloor instruments, then by the land network, and then by every person standing on the Pacific Northwest surface when the rupture begins. How much time would pass between those first instrument detections and the moment the shaking reached a city like Seattle? The answer is measured in seconds. A full Cascadia rupture and a segmented rupture do not produce the same map of destruction. The geography of impact shifts dramatically depending on which sections of the fault actually move. Understanding that geography helps explain why the segmentation debate is one of the most practically important questions in Pacific Northwest earthquake science. In a full rupture scenario, the fault breaks from its northern end near Vancouver Island all the way to its southern tip near the Oregon-California border. Every city along that corridor experiences maximum shaking. Seattle, Tacoma, Olympia, Portland, Salem, and the entire Oregon coast face the event simultaneously. Coastal subsidence occurs along the full 400 miles. The tsunami launches from the entire fault length, generating waves that strike the coast in multiple locations at the same time. Emergency resources across Oregon, Washington, and parts of British Columbia and Northern California are overwhelmed simultaneously. There is no unaffected nearby region to send help from. Every hospital, fire department, and search and rescue team within the impact zone faces its own local crisis at the same moment. In a southern segment rupture, the portion of the fault from roughly central Oregon down to Northern California breaks, while the northern section remains locked. Portland and the southern Oregon coast face severe shaking and subsidence. Seattle and the northern sections experience elevated shaking from the event, but at lower intensity than a full rupture would produce. A southern rupture of significant magnitude, perhaps a 7.5 to 8.5, would still be catastrophic for the communities directly above it, but the northern section of the system would remain intact and capable of sending emergency resources southward. The geographic scope of the disaster, while devastating locally, would be more manageable from a regional response standpoint. A northern segment rupture produces the reverse scenario. Seattle and the northern coast face the worst impacts, while Portland and the southern coast receive a more serious but survivable event. The coastal subsidence pattern also changes with rupture geometry. A full rupture drops the coast along its entire length. A partial rupture drops only the coast above the section that moved. Communities outside the rupture zone retain their current elevation and do not face the same permanent flooding risk. Tsunami generation follows the same pattern. A full rupture launches waves from 400 miles of fault. A segmented rupture launches waves from a shorter section, producing a more localized tsunami impact zone. Researchers studying past Cascadia events in the sediment record have found evidence suggesting the fault has produced both full and partial ruptures throughout its history. Neither pattern dominates conclusively. The fault has done both. For people living in the impact zone, the segmentation question is real and consequential. But for emergency planners, the full rupture scenario remains the standard planning basis, because designing for the worst outcome means that any partial event falls within the prepared response. Whether the fault cooperates with that planning is unknown. What is known is that the warnings scientists would receive before the rupture reached populated areas, and the warnings those populations would receive in return, are measured in seconds to minutes, and those seconds carry an enormous weight. When the Cascadia fault ruptures, a clock starts. It starts the moment the seafloor moves. From that point, the time between the initial rupture and the arrival of the first tsunami waves at the coast is fixed by physics. Water depth, distance from the fault to shore, and the shape of the seafloor all determine how fast the waves travel and when they arrive. For the Pacific Northwest coast, the estimated arrival time of the first tsunami waves after a full Cascadia rupture ranges from roughly 15 minutes to 40 minutes depending on location. Communities closest to the offshore fault, sitting directly across from where the seafloor moved, receive the least warning. Communities in protected bays further from the direct wave path may have slightly more time. 15 minutes is not enough time for most people to drive to high ground. Traffic on coastal roads during the shaking would be at a standstill. Bridges, many of which are on soft ground and face their own structural risks, may be impassable or collapsed. The roads themselves may have cracked, buckled, or shifted. The 2 minutes of violent shaking that preceded the tsunami arrival would have already disrupted the transportation network that evacuation plans depend on. This is why earthquake scientists and emergency managers emphasize a single, consistent message for people on the Pacific Northwest coast. If you feel strong, prolonged shaking near the coast, do not wait for an official warning. Walk or run inland and uphill immediately. The shaking is the warning. Vertical evacuation structures have been built in some coastal communities precisely for situations where lateral evacuation, moving inland by road, is not possible in the available time. These are reinforced concrete towers or elevated platforms designed to survive tsunami wave impact, where residents can climb above the projected wave height on foot within a few minutes from any point in the community. The number of vertical evacuation structures currently in place along the Pacific Northwest coast is far smaller than the number needed to shelter the coastal population. Construction has been ongoing, but demand far exceeds current capacity in many communities. The warning system itself has improved substantially since the 2004 Indian Ocean disaster, which struck without warning because no Pacific-facing detection network existed at the time. The Pacific Northwest now benefits from a network of offshore buoys and seafloor pressure sensors that can detect tsunami waves as they form and transmit alerts in real time. But the lead time that detection buoys can provide for a locally generated tsunami is limited. The Cascadia fault sits close to shore. The waves do not travel across the open ocean before reaching the coast. They begin reaching the coast within minutes of the rupture, leaving very little time for detection, transmission, processing, and public alert to occur before the first waves arrive. For distant tsunamis, warning systems work well. For a Cascadia-generated tsunami hitting the Pacific Northwest coast, directly the window is narrow. Seconds of warning may be achievable. Minutes of warning require both the detection system and the public to function perfectly under post-earthquake conditions. And the infrastructure that warnings travel through, the cell towers, power lines, and communication systems, faces its own severe test during and after a magnitude 9 rupture. The Pacific Northwest has been warned about the Cascadia fault for decades. Engineers, scientists, and emergency planners have published studies, held public forums, and briefed government officials at every level about what a full Cascadia rupture would do to the region's infrastructure. The findings have been consistent and clear. The infrastructure is not ready. Bridges are the most visible problem. Oregon alone has hundreds of highway bridges that engineers have flagged as vulnerable to a major Cascadia earthquake. Many of these bridges were built before modern seismic codes required earthquake-resistant design. Some sit on soft soil, where liquefaction and amplified shaking create maximum stress. Others cross rivers at coastal locations, where the combination of bridge damage and tsunami inundation makes post-earthquake repair particularly difficult. After a full Cascadia rupture, the Oregon Department of Transportation estimates that a significant portion of the state's highway network could be impassable for weeks to months. The bridges that cross the major rivers between the coast and the Willamette Valley, the routes that connect coastal towns to inland cities, are among the most vulnerable. If those crossings fail, coastal communities become isolated islands, surrounded by damaged roads and water, unable to receive emergency supplies or evacuate residents who need medical care. Water systems face a similar vulnerability. Water treatment plants, pumping stations, and distribution networks in both Seattle and Portland rely on buried pipes that run through soft sediment. Liquefaction during a major earthquake breaks pipe joints, shifts pipe sections out of alignment, and allows contaminated soil water to enter the distribution system. After the 1994 Northridge earthquake in Los Angeles, a much smaller event than a Cascadia scenario, water system damage left hundreds of thousands of residents without running water for days to weeks. A Cascadia rupture would produce far more extensive pipe damage across a much larger area. Electrical infrastructure presents another layer of the problem. Power transmission towers in the region were not all built to current seismic standards. Substations and switching equipment, which are difficult to protect against prolonged shaking and liquefaction, face elevated failure risks. Restoration of power after a major Cascadia event is projected to take weeks in the best case, and months in the worst case for the hardest hit areas. All of these infrastructure failures compound each other. A hospital that survives the shaking cannot function without water and power. An emergency shelter that remains standing cannot serve evacuees if the roads to reach it are blocked. A water treatment plant that needs repair cannot be fixed if the equipment needed to fix it cannot be transported to the site. Engineers and planners know exactly what needs to be done to close these gaps. Retrofit vulnerable bridges, seismically harden water and power infrastructure, build redundant supply routes. The estimates for completing this work run into tens of billions of dollars. Progress has been made in some areas and stalled in others. The gap between what the science says is needed and what has actually been done is where the real risk lives. And nowhere is that gap more human than in the survey data that shows how the people living above this fault are preparing for it. Emergency planners studying the Cascadia threat have one advantage that most disaster preparedness efforts do not have: a detailed physical record of the last event. The 1700 earthquake left evidence scattered across the Pacific Northwest landscape, ghost forests marking where the coast dropped, sediment layers recording the tsunami's reach inland, sand sheets deposited by the waves on riverbanks and estuary floors. Each piece of physical evidence is a data point that tells scientists what the fault did and what it is likely to do again. Researchers have spent decades mapping these features systematically. They walk riverbanks looking for the distinctive sandy layers that tsunami waves deposit when they surge inland. They core into coastal marsh sediment, pulling up cylinders of material that preserve hundreds of years of geological history in sequence. They date each layer and measure each deposit to reconstruct the precise behavior of past events. From this work, a detailed picture of the 1700 event has emerged. The tsunami reached up to 3 miles inland along some river valleys. The sand layers deposited by the waves are sometimes several inches thick, indicating the waves carried enormous amounts of sediment as they moved. In some locations, multiple sand sheets are stacked in the sediment column, each one representing a separate past event, each one a chapter in the fault's long history. Emergency planners use this physical record to check and calibrate their modern computer models. When a tsunami simulation predicts wave run-up to a certain distance inland, planners compare that prediction against the actual geological evidence from 1700. If the model matches the deposit, confidence in its predictions increases. If the model and the deposit disagree, scientists investigate the discrepancy and refine the model. The 1700 record has also revealed information about how quickly coastal communities would need to respond. By measuring how far tsunami sand traveled inland and how high it reached on slopes, scientists can work backward to estimate the wave height and speed at the shoreline. Those estimates inform the evacuation zone boundaries that appear on coastal warning signs today. One finding from the 1700 analysis has been particularly influential in modern planning. The initial ground drop during the rupture, the subsidence, happened fast enough that coastal residents at the time would have had very little warning that the ocean was about to surge. The land dropped, the shaking was still occurring when the water began to move, and the waves arrived before most people would have fully processed what was happening. The 1700 blueprint is the most valuable tool planners have for understanding what a future event will look like. The fault produced it once. The conditions that produced it have been rebuilding for 3¼ centuries. Comparing Cascadia to other megaquakes that have already struck during the modern era also reveals how a fully prepared response differs from what currently exists in the Pacific Northwest. And the country that provides the sharpest contrast is one that has already been through it. The 2004 Indian Ocean earthquake struck without warning on the morning after Christmas. A magnitude 9.1 rupture along the Sunda subduction zone generated one of the deadliest tsunamis in recorded history. More than 220,000 people were killed across 14 countries. The waves reached coastal communities in Indonesia within 15 minutes. They reached Thailand in about 90 minutes. They reached Sri Lanka and India in roughly 2 hours and still arrived with enough energy to kill thousands. The Cascadia subduction zone and the Sunda subduction zone share the same basic geological setup: an oceanic plate subducting beneath a continental plate, a locked fault, accumulating strain over centuries, a coastline sitting in the direct path of any tsunami generated by a rupture. The physics of the threat is nearly identical. The differences between the two scenarios reveal what the Pacific Northwest is actually up against. The 2004 event struck a region with very little formal tsunami warning infrastructure, limited public education about tsunami behavior, and minimal vertical evacuation options along most coastlines. The death toll reflected those gaps. The Pacific Northwest has better warning infrastructure, significantly better public education, and a growing network of vertical evacuation options. Those improvements matter and would save lives. But the Pacific Northwest also has infrastructure challenges the 2004 region did not face in the same form. Seattle and Portland are major metropolitan areas with millions of residents. Tall buildings on sediment basins, bridges and highways that face severe damage risk, and a population that depends heavily on functioning electricity, water, and communication systems. The urban complexity of the Pacific Northwest disaster scenario exceeds what most coastal communities in the 2004 impact zone faced. The 2004 earthquake also produced a different subsidence pattern. In some affected areas, the land actually rose during the rupture rather than sinking, depending on location relative to the fault. In the Cascadia scenario, coastal subsidence is expected to be more widespread along the Pacific Northwest coast, adding the permanent flooding dimension that the 2004 recovery did not face. Researchers studying both fault systems have also noted one sobering similarity. In both cases, scientists had identified the fault as capable of a megaquake well before the event occurred. The Sunda fault was known to be dangerous before 2004. The Cascadia fault has been known to be dangerous for decades. The difference between warning and preparation is where the lessons of 2004 apply most directly to the Pacific Northwest. Knowing the risk exists is the first step. Closing the gap between knowing and being ready is the work that is still incomplete. Countries that have navigated that gap most successfully offer a specific kind of blueprint, one built not on prediction, but on systematic, culture-wide preparation for an event that will eventually arrive. Japan has experienced more major earthquakes than almost any other country on Earth. The 2011 Tohoku earthquake and tsunami, a magnitude 9.0 event that struck off Japan's northeastern coast, killed nearly 20,000 people and caused catastrophic damage across hundreds of miles of coastline. The disaster exposed gaps in Japan's already extensive earthquake preparation and forced a comprehensive reassessment of how the country approaches tsunami readiness. Japan's response over the following decade offers the most detailed example available of what systematic, large-scale earthquake and tsunami preparation looks like in a modern society. The country rebuilt coastal defenses at a massive scale. Enormous seawalls, some reaching 40 feet in height, were constructed or extended along hundreds of miles of vulnerable coastline. These walls are not universally praised. Critics argue they create a false sense of security and may actually discourage the individual behavioral responses, immediate evacuation when shaking begins, that save the most lives. The debate over seawalls versus evacuation-focused preparation continues in Japanese planning circles. Japan also dramatically expanded its vertical evacuation infrastructure. Elevated platforms, reinforced multi-story buildings designated as official tsunami refuges, and new purpose-built evacuation towers were constructed in communities where running inland was not feasible within the available warning time. Public education in Japan became embedded in routine life. Schools conduct regular earthquake and tsunami drills multiple times per year. Children learn evacuation routes before they learn long division. Coastal communities practice the specific sequence of actions expected of residents in the first minutes after a major earthquake, without waiting for official instructions. Early warning systems in Japan were also overhauled after 2011. The country invested in a denser network of offshore sensors and upgraded the algorithms that calculate tsunami wave heights in real time. Today, Japan can issue a tsunami warning within approximately 3 minutes of a major offshore earthquake. For a locally generated tsunami, even 3 minutes is not always enough to fully evacuate low-lying areas. But 3 minutes with a prepared drilled population produces very different outcomes than 3 minutes with an unprepared one. What the Pacific Northwest can take directly from Japan's experience is a specific lesson about where preparation works best. Technology and infrastructure matter, but the single most effective survival behavior in a tsunami zone is immediate self-directed evacuation the moment strong shaking occurs, before any official warning arrives, before any alarm sounds. In the 2011 disaster, communities that had drilled this behavior regularly experienced dramatically lower death tolls than communities in similarly exposed locations that had not. The difference was not equipment. The difference was behavior. The Pacific Northwest has the geological knowledge, the scientific monitoring, and the institutional awareness to build a preparation culture comparable to Japan's. Whether that culture has actually taken hold in the communities above the Cascadia Fault is a question with an uncomfortable answer. A significant portion of Pacific Northwest residents are not ready for the Cascadia earthquake. Surveys of coastal and urban residents in Oregon and Washington consistently find that large numbers of people lack the basic supplies, knowledge, and plans that emergency managers consider minimum preparation for a major regional disaster. The specific gaps vary by survey, but the patterns are consistent. Many residents do not have a 2-week supply of food and water stored at home. Emergency managers recommend 2 weeks because that is the estimated minimum time before reliable external supply chains could reach isolated coastal communities after a full Cascadia rupture. Many residents do not know which tsunami evacuation zone they live in, which roads lead to high ground from their home, or where the designated vertical evacuation structures in their community are located. This information is publicly available on county websites and posted on coastal warning signs. The problem is not access to information. The problem is engagement with it. Survey data also shows that a substantial number of Pacific Northwest residents significantly underestimate the shaking duration of a major Cascadia earthquake. When asked how long they expect the shaking to last, many people answer between 10 and 30 seconds. The actual expected duration for a magnitude 9 rupture is closer to 2 minutes. That underestimate matters because people who expect 10 seconds of shaking may stop their protective behavior prematurely and stand up before the most destructive waves of ground motion arrive. Emergency managers point to several reasons for the preparation gap. Distance from a direct major earthquake experience plays a role. The Pacific Northwest has not experienced a truly damaging earthquake in modern memory, unlike Southern California, which has the 1994 Northridge event as a reference point. Without personal experience of severe shaking, the threat remains abstract for many residents. The scale of the recommended preparation also creates psychological barriers. 2 weeks of supplies, a family communication plan, multiple evacuation route options. The list is long, and each item requires time, money, and attention that competing daily priorities absorb. Emergency planners have shifted their public messaging in recent years to address this, breaking preparation into smaller, achievable steps rather than presenting it as an all-or-nothing undertaking. Store 3 days of water first, learn your evacuation zone next. Add supplies gradually. The goal is movement in the right direction, not perfection. The preparation gap is real and measurable. It is also closable. The knowledge exists. The resources are publicly available. The tools have been developed. What closes the gap is individual action, taken before the fault breaks, while there is still time to choose. And the instruments watching the fault are getting better every year at detecting what the fault is doing before it makes that choice for everyone. Science changed when the instruments moved underwater. For most of the 20th century, the Cascadia subduction zone was monitored primarily from land. Seismometers in Oregon, Washington, and British Columbia measured ground motion when earthquakes occurred. GPS sensors tracked the slow deformation of the surface as the locked fault strained the crust. Those tools were valuable, but they had a fundamental limitation. The most important part of the fault, the offshore locked zone that would generate the megaquake and the tsunami, sat under miles of ocean water where land-based instruments could not reach effectively. The installation of Seafloor observatory networks changed that. The Ocean Observatories Initiative, a federally funded program, deployed instrument packages directly on the seafloor off the Oregon and Washington coast, sitting on top of the fault and connected to shore by fiber optic cables that carry data in real time. The seafloor instruments include broadband seismometers, sensitive enough to detect tremors far too faint for land stations to register. They include pressure sensors that measure tiny vertical movements of the seafloor, fractions of an inch, caused by slow slip events. or minor fault adjustments. They include hydrophones that listen to the underwater sound environment, picking up the distinctive low-frequency signals produced by tectonic activity in the fault below. The data streams flowing back to shore from these instruments produce a continuous, high-resolution picture of the fault's behavior. Scientists monitoring the network can see slow slip events beginning and ending in near real time. They can detect clusters of microtremors too small to feel on the surface, but meaningful as indicators of stress patterns in the fault. They can observe how the fault responds to distant earthquakes, as seismic waves from events around the world pass through the Cascadia system. This capability did not exist a generation ago. A slow slip event in 1980, or whenever, would have gone completely undetected by the instruments available at the time. Today, the same event would appear on screens at university monitoring centers within hours of beginning, triggering automated alerts and human review. The improved detection capability feeds directly into the alert systems designed to warn the public when a rupture begins. Earthquake early warning systems work by detecting the first waves of motion produced by a rupture, called primary waves, which travel faster than the destructive surface waves that do the damage. By detecting primary waves first, the system can calculate that a damaging earthquake is underway and issue alerts before the surface waves arrive. The Shake Alert system, now operational across the Pacific Northwest, uses this principle to send automated alerts to phones, computers, and connected devices when a significant earthquake is detected. For an event on the offshore Cascadia fault, the Seafloor instruments would detect the rupture first, feeding the earliest possible signal into the Shake Alert calculation. How much warning that translates into for a person in Seattle or Portland depends on where the rupture starts and how fast it propagates. The physics does not allow for very long windows, but every additional second of warning at the scale of a major urban population translates into lives. The Shake Alert system cannot stop the earthquake. What it can do is compress the reaction time between rupture and response. When a Cascadia earthquake begins on the offshore fault, primary waves travel outward from the rupture point in every direction. These waves move through the Earth faster than the destructive surface waves that follow. The difference in travel speed between primary waves and surface waves creates a window, measured in seconds to low minutes, during which a warning can be issued and received before the worst shaking arrives. For a person in a coastal community close to the fault, that window may be very short, perhaps a few seconds. For a person in Seattle or Portland, further from the offshore fault, the window is somewhat longer, potentially reaching 30 to 60 seconds in some scenarios. 30 seconds sounds trivial. For a trained individual in the right context, it is not. A surgeon 30 seconds from the worst shaking can step back from an operating table before the shaking makes precise work impossible. An automated system 30 seconds ahead of shaking can pause a train before it enters a tunnel. A traffic signal system 30 seconds ahead can stop vehicles from entering a bridge. An elevator 30 seconds ahead can open its doors at the nearest floor before the shaking traps occupants between levels. For ordinary people in homes and offices, 30 seconds allows enough time to drop, cover and hold on, to move away from windows, to wake up and get under a sturdy surface. These behaviors, done at the first alert rather than at the moment shaking begins, improve survival outcomes. Shake Alert sends alerts through multiple channels simultaneously. Wireless emergency alerts to cell phones, the same system used for Amber Alerts and severe weather warnings. Connected devices registered to the system. Automated industrial controls integrated directly with the earthquake warning feed. The system has been tested against real earthquakes in the region and has performed within its design parameters. The limitation is not the technology. The limitation is the physics of a locally generated subduction zone earthquake striking close to the coast. For coastal communities within 15 miles of the fault, the warning window may be so short that individual action is the only reliable option, independent of any electronic system. The earthquake itself, felt as prolonged, intense shaking is the most reliable alert those communities will receive. The consistent guidance from every seismologist and emergency manager studying this fault is unchanged. Strong shaking near the coast means move immediately, without waiting for confirmation, without waiting for a phone notification, without waiting for an alarm. The people who survive close-in tsunami events in well-studied historical disasters are overwhelmingly people who acted on the shaking itself as their signal. The warning technology is real, and it saves lives further from the fault. Closer to the fault, survival depends on what was decided before the earthquake started, the evacuation routes chosen in advance, the supplies stored, the behaviors practiced. All of it leads back to the single question that science cannot yet answer, the one that sits at the center of everything researchers know and do not know about the Cascadia subduction zone. Scientists know the fault will break, they do not know when. That statement is not an admission of failure. It is an honest description of the current boundary of earthquake science, and the Cascadia subduction zone sits directly at that boundary. The fault has been locked since January 26, 1700. The Juan de Fuca plate has moved approximately 54 feet since that night, all of it stored as strain in the crust above the locked zone. The historical record shows the fault ruptures on a cycle of roughly 200 to 500 years. 325 years have passed. The probability of a major event within the next 50 years sits at 37% and growing. Every piece of evidence points in the same direction. The fault is loaded. The strain is real. The rupture is inevitable on a geological timescale. What no instrument, model or dataset can determine is the specific day, month, or decade when the friction holding the locked zone together will finally fail. Earthquake nucleation, the moment a rupture actually starts, happens at a scale and speed that no current technology can predict in advance. The fault will give no dramatic surface warning, no rising ground, no visible crack, no obvious signal visible to the naked eye. The first indication for people on the surface will be the shaking itself. The recent signals from the fault, the slow slip events, the offshore earthquakes, the stress alignment along the southern section, are meaningful data points in a long-running scientific investigation. They confirm the fault is active and stressed. They do not predict timing. What that leaves for the millions of people living above the Cascadia subduction zone is a choice about how to exist inside an open-ended window of elevated risk. Every day that passes without a rupture is a day the probability slowly increases. Every year of continued locking is another year of strain accumulation. The window is open, and there is no way to know when it will close. Some people find that uncertainty paralyzing. Scientists who have spent careers studying this fault tend to find a different response more useful. The uncertainty about timing is not a reason to stop preparing. The certainty about the outcome is. The fault will rupture. The tsunami will launch. The coast will change. Those facts are not in dispute. What remains in human control is everything that happens in the time between now and that rupture. The bridges that get retrofitted, the evacuation routes that get learned, the supplies that get stored, the drills that get practiced, the building codes that get enforced, the vertical evacuation towers that get built. The young people who grow up in coastal Oregon, knowing that if the ground shakes long and hard, they walk uphill, without waiting for anyone to tell them to. The Cascadia subduction zone has been silent for 325 years. Its silence is not peace. It is pressure. It is stored energy with no outlet, building steadily beneath one of the most beautiful and inhabited coastlines in North America. The question science cannot answer is when. The question every person living above this fault can answer is whether they are ready.